Okay. So we're looking at function behavior, continuing our look at function behavior. Review, I guess I should say, of function behavior. We're going to talk about zeros and roots today. All right. And then we'll also talk about like increasing, decreasing, and constant behavior of a function too, identifying those on the intervals. And like I said, we'll probably take a look at a little bit more of those piecewise functions just because they were so much fun earlier. And I think we could probably use some extra help because piecewise functions will probably appear on your test in a week, okay? And we need to get better at them because they like to use them in calculus as well a lot. Okay, so the zero or root, zeros or roots of a function are points where the function, what? Think graphically. The zero of a function or the root of a function or root of a function are points where the function does what? Crosses the axis, originates. Now is that what you're going to say too?
Yeah, I was going to say crosses the axis.
And specifically we're going to say crosses the x-axis. Yeah. We're not so weak. I mean, y-intercepts are important too, and they have like their own context of meaning. But a zero or a root, I really am talking about where the function intersects the x-axis. Okay.
That could also be called the solution, couldn't it?
It really depends on what. I mean, solution I think is a more broad term because you think of like it depends. It depends on what you're looking for there. It could be a solution, yes. All right, to find a zero or root. Okay. Well, if we know it's where the function intersects the x-axis, what do we know about points on the x-axis? What's always true about a point on the x-axis? Y value is 0, right. So in order to find a 0 then, we're going to use that. We're going to set the function equal to 0. We're going to use that to our advantage.
Because f of x is the same as y.
It's like exactly right. They're kind of interchangeable. Okay, oops, I should say set the function equal to 0 and solve for the variable. Okay. So let's do a couple examples here together, and then I'll do 2 together, and then we'll have you guys try 2 on your own. Okay. So find the roots of the following. Right. F of x equals x squared minus 5x plus 6. I know we haven't really reviewed factoring and stuff like that, but it is something you've seen since Algebra 1 at least. So, you know, it should be something that we kind of have, but we will review it some too. But I am kind of putting the cart before the horse right now. Okay, so we'll set it equal to 0. Okay, and at this point, how do we solve this equation? What do we have to do? Anybody? Factor, that's right. So, let's see. Since it's quadratic, most likely, if it does factor,
2 and 3.
it's going to have 2 and 3, positive 2, positive 3?
Or negative 2, negative 3.
Negative 2, negative 3?
1 negative 6.
1, negative 6?
No.
Negative 2, negative 3.
Negative 2, negative 3. Yeah, so this kind of quadratic, I feel like, for whatever reason, can throw students for a loop. I think because like the 2 and the 3, but there's also like the 6 and the 1, and so depending on whether these are positive or negative there, it can like kind of change your answer. But yeah, so this one, we need, again, our two numbers to multiply to positive 6, so negative 2 times negative 3, positive 6, but then they're going to add to make negative 5, which is exactly what we wanted there. So there's our answer.
Oh, right.
And so we get x equals 2 and x equals 3. Yes? Okay. that is a fine answer. You can also, if you want to, write that as 2, 0, comma 3, 0, okay? But you don't need to, okay? You don't have to. And remember here, right, we're taking advantage of that zero product property. This product is equal to 0, and so when two things multiply to give you 0, that means one of those two things has to be 0, right? If I had a problem, if I had a problem that looks like this, okay, this does not then guarantee that x minus 2 equals 2 and x minus 3 equals 2, right? Does not follow necessarily. 2 is not as special as 0 is, right? 2, you can multiply all sorts of combinations of numbers to get 2. 0, in order to multiply two things to get 0, one of those two things has to be 0. There's no way to multiply to get 0 without one of them being 0, okay? Here, though, there's all sorts of combinations, so this is not, it does not follow there that you set those things equal to 2, okay? It's called the zero product property. So you need to make sure that when it's equal to 0, you can break it up, but not when it's not equal to 0. All right. Again, just a common mistake that I see students make sometimes. All right, let's try another one. H of x equals 3 over x squared minus 9. Okay? H of x equals 3 over x squared minus 9. So the next to last column should be for the stuff that was due. So this would be the book work, and then this would be the worksheet over here. Yeah, I'll try to make that more clear. Okay. All right. So, what are the zeros for this function? No zeros? How'd you determine that, Ethan?
Because you can divide 3 by anything to equal 0.
So okay, right. So we're going to set this thing equal to 0 because that's what we do when we want to find a 0, right? We set the y value equal to 0, and we try and see when does this equal 0. Mm-hmm. We're trying to figure out when this is equal to 0. So for what x value it would equal 0, sure. Multiply both sides by the denominator? Yeah, absolutely we can. And we would still get 0 equals 3, exactly. So what is that going, what does that result kind of tell us then?
I don't know. You took it back.
I did. Okay. So those cancel. Correct. So what does it mean? That means there's no solution, right? There's no solution. This is not true. So our original assumption that this is going to equal 0 is also not true. There are no zeros. And you can put an E or not an E, I guess.
So I guess it's done then.
All done? Everyone got the paper okay? For both columns? Okay. There you go, sir. Thank you, Simeon. And you can just put that one other. Yeah, it's right to the very outside there. That's great. Yep. Okay. Right. Another way you can think about this is this function here, we might call it a rational function. It's really just a fraction, right? A fraction equals 0. So a fraction here only equals 0 when what part of the fraction is 0? When the numerator is equal to 0, the fraction is equal to 0, right? And when the denominator is not 0, of course, at the same time. Well, 3, like, again, with Ro kind of pointed out there, right? This 3 will never equal 0. We end up with the same kind of result, right? And so there are just no zeros. This thing never intersects the x-axis. Okay, that's the idea there. Never intersects the x-axis. Okay? So for rational functions, you want to set that numerator equal to 0. Okay? So I'll write that here. For rational functions, set the numerator equal to 0. Question?
Why can't we square 3?
Yes. Yes, there should be 3. Okay. So here's 2 for you to try. G of x equals the square root of the quantity 2x plus 5 over x minus 2. And m of x equals x squared minus 2x over x cubed plus 3x. Okay? So find the zeros for both of those, please. Or the roots, if you like. Okay. These are both rational functions, so use that to your advantage here, you know. Don't feel like you have to take it all at once. Use only the information that you need.
So do you always factor?
You want to know when it's going to equal 0, so you have to do whatever is necessary to solve it.
So just set numerator of rational functions.
Equal to 0. And so in the first one, you don't have to factor. The second one, you do need to factor there, right? Okay. Anyone still need more time? Yeah. Are you on the last one? More seconds here. Go over it.
Zero squared is 0, right?
0 squared is 0. Okay, here we go. Ben, you got an answer for us for number 3? Negative 5 halves? Okay, x equals negative 5 halves. Okay. I froze it. There, it's unfrozen. Okay. Good with that? Any questions? Sure. Okay, so Ben, what'd you do here?
Neither the top had to be 0, so just set it to 0 and then solve.
Okay, yeah, it sounds like legit, you know what you're supposed to do. Yeah. Set the numerator equals 0. Square both sides, 2x plus 5 equals 0. Subtract 5, divide by 2, x equals negative 5 halves. Okay. So the bigger thing, right, is when we put this all together, you're going to need to be able to identify zeros. You're going to be able to identify, domain restrictions and stuff like that too, okay? And not getting confused about what to do when, okay? So it's super important that you have in your head, okay, when we talk about domain, that's what we're looking for x values that will cause problems. Square roots of negatives, dividing by 0, that happens here, okay? So domain, you'll do that separate thing. But then also as part of, a problem like this, you could be asked to find the zeros. That's a different kind of, item or object, or something, or calculation you'll do, because the 0 is when the function equals 0, right? And so that's when the numerator equals 0, and solve from there. And some of these things are they look similar to each other too, so it can get kind of confusing. Students do sometimes get mixed up. So you got to keep all those things straight in your head. When I'm asked to do this, I got to do this. When I'm asked to do this, I got to do this, and all that stuff. So, Jeff, question?
Could you go back to the quadratic you solved while I didn't have a pencil?
Yes, there it is. Okay.
I'll just write it down and I can solve it on my own.
Gotcha.
X squared plus minus 5x.
And then let's go to Brendan. Brendan for number 4. All right, what'd you get for the zeros there?
I didn't get that one.
Didn't get that one? Okay. All right. Let's go to Adri. Were you able to get that one, number 4? No? Oh, okay. Let's see here. Molly, did you get number 4? No? Okay, we'll keep going here. Chrissy, it's back to you. X equals 2 and x equals 0, question mark? All right. How about, let's go here. We'll stop. What do you think? Yes, x equals 2, x equals 0?
Yeah.
Yeah. Okay. All right. X equals 2, x equals 0 it is. Okay. No one wants to say anything about those two.
Do you have anything to say?
Yeah, that's
I,
your answer.
I do, but I mean.
Then if we're wrong, then you can tell us.
There is a problem with one of these two answers. I'll give you that much of a hint.
Zero?
Okay, so why? If you think it's 0, why 0? Were you just guessing?
I'm guessing.
No, okay.
Because I know you're not going to
There's a problem with one of these two answers.
or negative 2.
Can you divide 0 by 0?
Ah, right, yeah. So what is 0 divided by 0? It's also kind of that's what you call indeterminate form. So that's kind of different than undefined, but still the idea here is that if we go back to talking about our domain and domain restrictions, is 0 in our domain? No. Okay. Why not? If 0 goes in the denominator, you get 0. Okay. And so 0 is not a domain. Is not in our domain. Therefore, it's not a possible x value that we can use in our function. So then, what should we do? This x equals 0.
Just throw it away.
Throw it away. Exclude it. Right. Okay. So not in the domain.
If there was like a +1 in the denominator, could we include it?
Yes. Yes. If it was, yes, absolutely. Otherwise, you would include it. In this case, we have to throw it out because 0 is not in the domain. Okay. So long story short, right? We have to keep our eyes a little bit wider than maybe we have, right? So in the past, right? So just prior to this problem, we were focused in, zoomed in on, hey, just set the numerator equal to 0, we're good to go. We have to widen our view a little bit here to also we also have to check our domain restrictions though, because if it's not a domain, it shouldn't really count as a 0 because it's not possible. Okay. Let's keep going here then. Okay. And also, if you thought that might be the possibility, please feel free to speak up next time too. All right, it's okay to say that kind of stuff as well. All right, feel free to do that. But maybe no one really did want to speak up there, and that's fine. I'll make sure we hit the important stuff. Right, that's my job as the teacher. Okay. One other thing I want to talk about here is just talking about intervals of increasing, decreasing, and constant. I want to just jump right into an example. So we'll just jump right in. For what values of x is the given function? Increasing, decreasing, or constant. That kind of covers all the bases, I think. I guess you could have like it wouldn't be a function if it was undefined, so never mind. Okay. For what values of x is the given function increasing, decreasing, or constant? Okay. Let's see here. So first of all, just a real quick recap, right? Increasing means what's happening in the function if the function's increasing. Okay, so it's going to the right. Okay, what's happening as you go to the right? The function goes up, right? So as your x values increase, your y values increase. As your x values decrease, what should happen to the y values? They should decrease as well, simultaneously, okay? So as you go to the right, your x values are increasing, your function will be going up, y values increasing. If you go to the left, so again, to the right, increasing, but also to the left. If the y values are decreasing, that's still an increasing behavior because you read increasing from left to right, okay? And then decreasing is the exact opposite. You know, from left to right, your y value should be going down. And then constant means what? It's just what kind of line? Horizontal line, yeah, because we're going to be careful. Lines can be increasing or decreasing, right? But yes, constant is a horizontal line, which is like exactly the meaning of constant too, right? If something is constant, it is unchanging, not increasing, not decreasing, flat, right? So it's like that's what constant means. Okay, so let's h of x equals the absolute value of x minus 5. We don't need a calculator for this, right? We know what this graph is going to look like. It's the graph of the absolute value of x, but under what transformation? Right? 5, okay. And so you can, even if you want to, you can like graph a little, do a little sketch for yourself. That's part of the reason why we learned these like parent functions. Okay, so something like that. Okay. Something like that. So, okay. Molly, is this function ever increasing?
Yes.
Okay, where? From what? Okay, so we'll use x values to describe this. So at what x value does it start to increase? X value. That's okay. What's the x value, sorry? 5. That's right. So I'm going to abbreviate here. Increasing. I'm going to recommend you don't include the end point here in this case. So I'm going to say parenthesis 5 to infinity. Okay? Because kind of like at 5, it's kind of unclear about whether it's increasing or decreasing. From the right, it looks like it's increasing, but from the left, it looks like it's, the other behavior there. Okay, decreasing. All right. And so then what's the interval of where we are decreasing? Let's go to Maddie G. Decreasing. What's the interval of decreasing there?
I'm not
Okay,
sure.
so where does it stop decreasing? How about that?
It stops decreasing at
What x value?
5.
5, okay. So we know that's our endpoint there. And then it's decreasing forever to the left there.
Yeah.
So then what would this be?
Negative.
Negative infinity, you got it. Roy, question?
No.
You're just looking to answer? Help out?
No.
Okay. Stretching? Okay. So yeah, negative infinity is a 5, decreasing. Be careful, right? Because we can like look at this and think in our brains, oh, it's going up. That's increasing, right? Because like the arrow's pointing up, Mr. Wade, that's increasing. And like, yes, in some, in non-math scenarios, you could say that's going up, right? So therefore increasing. And you might not be wrong there. But if we're really reading this from left to right, it is going down from left to right. And that's the important thing. You have to orient yourself, according to the mathematical definition. We're going down from left to right, and they go up from left to right. So it decreasing, then increasing. Okay. All right, let's look at another one here. I'll use h of x again, and this will be the last one we look at here, and then I'll take a look at a piecewise function or two. 2 parentheses x minus 1 cubed plus 7. Okay. All right, what's our parent function here? X cubed, okay? So you want to picture in your mind what x cubed looks like. What kind of transformations are happening to this function? What kind of transformations do we see here? Anybody? Up 7 and right 1. Okay. And then there's a 2, which is just like a vertical stretch of 2.
Yeah.
Okay. So, just think about what the graph of x cubed looks like, but shifted right 1 and up 7, and with a stretch of 2. Are we going to be increasing at all in this interval, or in the function? Yes.
Yes.
From what to what?
Negative infinity to infinity.
Negative infinity to infinity. Yeah.
It's always increasing.
What's our interval of decreasing?
There is never.
Never. Yeah, it does not exist, right? So never. And then constant as well. It's never going to be constant either. Okay. I guess I can put that here. Constant never. I didn't really put constant up here. So in your mind, if we picture that x cubed, what we have right there, I should say. So here's the parent function for x cubed.
It never goes from left, left down.
Right. Yeah. For this kind of thing, all it's going to do is take this. Yes. Exactly. All it's going to do is take this, shift it right 1, and then up 7. So I don't know, somewhere up here, and it's going to look like this. And the 2 will stretch it some, but the idea is it never decreases.
Yeah, I was just confused because isn't there arrows on both sides of them?
Oh, yeah.
That's why I thought it would decrease.
So right, it is going down, but you have to, when you're talking about increasing and decreasing, for both of them, you have to read it from left to right. What's happening as you go from left to right? So from left to right, we're increasing. Yeah. It gets a little disorienting with that, so you want to make sure you're careful with that. Mm-hmm. Okay. All right. So let's get out our little piecewise papers, if you don't mind, from 2 days ago, because I want to talk about 1 or 2 of these here on the back, and I forget which ones we did. I think, did we do 1, 2? Did we do 2, 3, and 4 together? Okay, so it's this.
4 together, 1, 2, 3 by ourselves.
You had us do 1 and 2 on our own, but then we went over them and we did 4 together.
Oh, like this then? Yes. Okay, because I did I think 3 with my other class, so that's why I got confused. Okay, so we'll flip over to the back here, and if you want more practice with like this, like if you want me to go over 3, I'll do that later when I'll give you guys a choice about whether you want to watch that part or not. But this I do want to talk about here, the exact opposite of the piecewise. Okay, so we talked about the piecewise functions, taking the piecewise, graphing it. Now we're going to take the graph. We're going to take the graph and write it as a piecewise function itself, right? Take the graph, write it as piecewise. Take the graph, write it as piecewise here. Okay? And so for this one, okay, we'll just look at number 5 maybe, okay? I want to talk about that. So we have 1, 2, 3 pieces. So our piecewise function is going to have, and I'll just use f of x, I guess, 3 parts to it. I'm going to kind of leave myself some space there. Okay. Now, all 3 parts are, these aren't going to quite join up. If you keep going up 1, right 1, up 1, right 1, up 1, right 1, they're going to be parallel. They're not going to quite join up.
No, yeah, but, oh wait, that was the third minus.
Doesn't quite match to this. I'm glad that you're looking for that, though, because there would be cases where that might be possible, but in this case, it is 3 separate things. And you could just do it 3 separate things, too, if you wanted to, even if they would line up, kind of thing. Anyway, let's look here. Okay, so this first piece, okay, what do we notice about this line? For example, yeah, it's only increasing there. The slope I know it doesn't, we're going to call that a slope of 1. Okay. Yeah, if you look further down, it doesn't quite line up there, but we're going to do it because otherwise it's going to be, I don't think we have enough information there otherwise. So we'll say it's got a slope of 1. So we'll say 1x, okay? What's going to be the y, what would be the y-intercept if we continue the line on? 1. So we can just say 1x plus 1 there. Okay? Comma, now we have to give our constraints. Okay, our constraint.
Wait, why is it a plus one? You have to-
Because if you keep going up 1, right 1, it will eventually, it would intersect the y-axis there.
You have to stop at -1.
Right. So we'll say x less than or equal to. How do I know to put the equal to there? It's got the filled in dot. So x less than or equal to -1. Okay, so there's that first piece. All right. The second piece, it's a line again. What's the slope of that line? 1. What's the y-intercept? 2. So it's 1x plus 2. Now for this one, where does it start? At what x value does it start? -1 less than x less than 1, right? No equal to's here. We can make a compound inequality. It's between -1 and 1, so we'll just say that. Between -1 and 1. There it is. Okay. And then the second piece. What's its slope? Looks like 1 again. Easy. What would its y-intercept be? Yeah, 0 if you were to continue it on there. So we can say plus 0, or you can just leave it 1x, comma, okay? And then for here, we'll say x values greater than or equal to 1, just like that. Okay? So it just breaks into individual pieces. All right. Let's do number 7, because that one's also, it's got a quadratic in it, so that'll be helpful. Okay, so we'll do this one. Number 7's got 2 pieces, quadratic piece, and then the linear piece right here. Okay. How is x squared, how is the parent function x squared transformed here to arrive at this? Okay, right, so we'll worry about the constraint on it, for what x values it exists, but I should say, how is it, transformed?
It's moved left, right?
Okay, so left 3, right? That looks like it's going to be the vertex there, right? It looks like it's bottoming out, so that we probably can say is the vertex, so it shifted left 3. So to do that, we're going to write parentheses x. To shift it left 3, we're going to do x what? Plus 3 squared. Is it shifted up or down at all? Nope. So just x plus 3 squared. Okay. Comma, what are our constraints? Where does that x plus 3 squared start? -3, and we'll include it, right? And then up to what? -1. Now, here's the thing. You have some choice here. Okay? Clearly, these two parts join together. You can decide if you want to include the -1 with the quadratic piece, then you need to exclude it from the linear piece. Or if you exclude it from the quadratic piece, you need to include it with the linear piece.
Well, let's just include it with the linear piece.
So exclude with the linear piece, is that what you're saying?
Yeah.
Okay, so include their -1. Okay, so we'll have the equal to with the -1. But then for the linear piece, which by the way, what is the slope here? You were right, -3 over 2. We're going down 3 and then right 2. So -3 halves x, and what's our y-intercept there? 2.5, right, or 5 halves if you like. Okay, and this one will start at -1, but we're not going to include it. Okay, but we will then go up to what? 3, and we'll include that 3. Okay. So there it is. I'll leave the rest to you to try on your own if you would like for more practice, okay? There's that other piecewise function to graph too on the other side of your paper. So those are for you to get extra practice if you like.